Assalamu alaikum, dear student. I hope you are fine and doing well. Today is our 22nd lecture of public key cryptography. Our last class, we have discussed RSA and some examples and some of its implementation and correctness proof of RSA. Today, we will discuss some modification of RSA over non-commutative structures. I mean to say RSA over matrix algebra. So this is quite helpful for student who and those who would like to start uh, who want to devise some public key crypto system or who want to what you call the apply it on some digital medium. So in that case, dear student, more or less, if I can take very simple digital medium like image, digital image, it's in the form of matrices. So in that case, dear student, RSA, our matrices, one of the important crypto system or one of the important modification of RSA that will ultimately utilize efficiently and easily in digital media. So what you have to do is to convert your digital image, which is in the form of layers and layers are in the form of matrices. You have to convert this into a chunks, and each and every chunks is consist of matrices of pixels. So let me elaborate this with the help of some example and some theoretical results. So dear student, while devising some modification of RSA over the matrix algebra, so the fundamental matrices group is general linear group or special linear group, and we will devise what you call the some fundamentals of general linear group, how the order of general linear group can be calculated, and which are the expression, how one can calculate the order, and how for different primes we can get this modification of RSA. Let us say RSA for three integer. More or less, we will discuss RSA for two integer. It can be extended to PQZ, where P, Q, and Z are also prime. So you can extend this RSA not with just two prime. It can be extended to three primes. Like if we have three primes, like P, Q, and Z, and P is 3, Q is 11, and Z is 30. In that case, dear student, ultimately your ring, order of your ring will be large as compared to if you can take just P, 2, P, and Q. So in that case, if you can see phi of n is also very large, it means the unit element in this ring Z1001 is more number of unit element as compared to if you can take only P and Q, that is 77. So if you can choose B as 79 using the algorithm one, A is 319. So in that case, A into B is congruent to 1 mod phi of n. It means in previous classes, if you can see over here, like this one, this is basically your what I should say E, and basically A is your D. If I can use same symbols as I have used in my previous lecture. So B, if you can replace this B with E and this A with D. So A into B, I just take A and B. So I just elaborate this example with A and B. So A into B is congruent to 1 mod phi of n. Then in that case, the pair of key n and b is public, and the while the A is your private key. So to encrypt the message 52, B uses algorithm for modular exponentiations at C m to the power b mod n. Then then in that case, this is 869, and then it's sent to the this to the A, which is receiver, and what A will compute? A will did C to the power A mod n, which is like this one, this 52, and which is your actual plain text. So matrix extension of RSA. So if you have like two prime P and Q, and you want to multiply this with, you will get 2 lakh 50,997, and then phi of n is like this one. If you get the E 19 and D is like this one, so the result is they are both are relatively prime under phi of n. So in that case, E and n is your basically public key. So you will get like this is your message. So how you will do it? You will have just to convert your message like this one into a like chunks of four, and take it divide this very large what you call plain text, this one, into a chunks like this one, m1, m2, m3, m4. So in that case you will have to separately apply RS on each and every element, each and every chunks. So if, the decryption is also applying in 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 a chunk wise. So you will have to apply the decryption, which is a reverse procedure of encryption on this each and every element. But this is more or less tedious how we can convert uh, this methodology into a matrix extension. So if we can convert this into a matrix extension, it will be quite easy for us to calculate, instead of calculating like for separately we'll have to calculate RSC for each and every element. So it will be quite tedious. Let us do some matrix extension for this problem. So it will solve your problem in just a one or two binary operation, one or two operation. So let us, before developing matrix modification of RSA, let us take one. So if you have 2 by 2 matrices, the order of the 2 by 2 matrices like this one. If you have one matrix that is base under modulo n, which is p minus 1, p which is n is like this, p into q, where p and q are distinct prime. So if you want to replace the plain text m with 2 by 2 matrix, the we call it as an m, rather than playing with phi of n, p minus n, we will instead rely on this expression, because the order of such matrix will be p square minus 1, p square minus p, q square minus 1, q square minus q. In that case, if you can see over here, we have the, this is the order of general linear group of 2 by 2 matrices, our P, and this expression, this from here to here, like if I can highlight it with the spotlight. So this one, like this one from this to this. This is the basically order of general linear group, our ZQ 2 by 2 of matrix 2 by 2. So in that case, if I can say general order of general linear group of order S is denoted by this one. This is general linear group of order S under mod N is invertible as bias matrices containing element from Zn with respect to multiplication. So the determinant of matrices are relatively prime and are relatively prime. So in that case, the we'll have a number of element in general linear group of order Zn, and it can be decomposed into a prime like this one. If I can say, like if you have uh, this is what you call the the expression for general linear group, general expression for general linear group. If you can say this one like this one, sorry. So it should not be multiplication. I just omit this one and I like this one. So the if ZP and ZQ, if you have a general linear group of our ZP and ZQ, their order is like this one. So the order of general linear group of order S can be decomposed into a product of P as well as. This is the basically the order of general linear group of order S our P, and this is again the order of general linear group of order S our Q. So if I select S is 2, means to say 2 by 2 matrices. So in that case, G is like this one. So we are going to develop general linear group our Zn of order 2, means to say how we can write extend our RSA, our GL to our ZN. So the order of general linear group of order 2 our ZP is like this one. So order I means how many matrices you can of 2 by 2 you can construct whose element are from ZP and whose determinant is non-zero. So let us take another simple result that is like if you have M from general linear, then the M from general linear Z2, ZP, and M is also belong from general linear uh, group of order 2, our ZQ. It means general linear group of order 2 Zn is isomorphic to general linear group of order 2 our ZQ into general linear group of order 2 our ZQ. In that case, we can say the order of this, what we call, let M belongs to this one, be the matrix made up of negative integers such that n is then n let gp is the order of gp. General linear group of order 2 over zp is p square minus 1, p square minus p, and general linear order of general linear group of order 2 over zq is zq minus 1, q square minus q. Then we can define the order of general linear group of order 2 over zn is like g is equal to gp and gq. So let us consider the E and D belongs G plus and such that E into D is one congruent to mod G, and let C is M to the power E mod N and D C to the power D congruent to 1 mod N. Let us take one very trivial example that P is 503 and Q is 499 and calculate N, and GP is P square minus 1, P square minus P. So we have so that number of 2 by 2 matrices, our ZP was determinant is non-zero. So similarly, GQ is like this one, and G is the product of these. So finally, we will have to select exponent E, which is 241, and find the decryption exponent D corresponding to this E, which is this, and we will like multiply both of E and D, and which is congruent to 1 mod G. It means E and D are inverse of each other, and this D is basically our public private key or the decryption exponent. Like in previous example, we have decomposed our message into 4 chunks, that is M1, M2, M3, and we have separately apply RSA. But here we don't apply separately RSA, but we take this 4 chunks as a matrix of 2 by 2, because to general linear group of order 2 our Z Zn, we are using general linear group of order 2. It means all 2 by 2 matrices. So message can be written as a 2 by 2 matrices in general linear group of order 2, our Zn. So we take C to the power E, which is E like this one, and take it as a mod n. We'll simplify it like this. So how we can decrypt? So C to the power D, which is this one, and we just apply operated on this apply modular operation, we'll get back our message n, which is our plain text. So dear student, if you can look over here, go back. So here you can see we will apply each and every on each and every element we will have apply RSA. But here if you can look over here, like this, we just make it as a matrix and take matrix to the power sum E, and then matrix to the power sum D. So this is the easiest way as compared to apply RSA on each and every element when your N as well as P and Q are very very large. So this is one of the what you call the extension of RSA or matrix algebra. These are some references which I have used in while what you call the making these slides, and these are also some research article which I have utilized while developing these slides. Till then, dear student, Allah Hafiz. May Allah bless you all. Allah Hafiz.